An Alternative Approach to Artificial Gravity. Theory by Rich Golden of Lincoln, Nebraska. Currently, the International Space Station orbits at an altitude of approximately 400 kilometers and travels at a velocity of 7.71 kilometers per second. Now imagine two 4-kilogram masses, though the exact mass does not matter so long as they are approximately equal. Each of these masses are connected to the space station by a 10-kilometer tether. One mass, which we will call the lower mass, is 10 kilometers closer to the Earth than the space station at an altitude of 390 kilometers. The other mass, which we will call the upper mass, is approximately 10 kilometers further from the Earth than the space station, giving it an approximate altitude of 410 kilometers. For the lower mass to maintain alignment with the space station, it has to travel at a velocity of approximately 7.70 kilometers per second. This velocity is insufficient to maintain orbit and without a balancing force would drag the space station out of orbit. For the upper mass to maintain alignment with the space station, it has to travel at a velocity of approximately 7.72 kilometers per second, a velocity that is too great for the upper mass to remain in orbit at that altitude. This creates an outward force which balances the force generated by the lower mass. What's important to note is that anything within either of these masses is experiencing an apparent yet insignificant gravity-like force, each in their corresponding directions. If we were to take that 4-kilogram lower mass and multiply it by 5, making it a 20-kilogram mass, it would clearly throw the entire system out of balance and drag the space station out of orbit. How do we balance these forces? The obvious way would be to increase the upper mass in a similar fashion, but this again would leave us with two areas of insignificant gravity-like forces. Instead, if we lengthen the tether to the upper mass, we can create a balance without changing its mass. This is important because as we lengthen the tether, the gravity-like force increases, hopefully to a point which could be significant enough to give our astronauts a place to exercise without elaborate equipment. 50 or even 100 plus kilometers may be necessary to achieve sufficient force, which sounds like a lot until you consider the alternative, making the 400-kilometer trip to Earth and needing a rocket to return to the space station.